Welcome back. In this video, we'll look at the acoustics of speech and look at some different ways people modify their voice. Okay, so let's jump over to here and go like that. The acoustics of speech. So just to review real quick, we've seen some basic audio toolkits like Audacity and Pratt. We've seen a little bit about the basics of acoustics like sounds and waves and how sounds are waves through a medium, right? Air, in our case, the vast majority of the time. Basic phonetics like segments, that is sounds, individual sounds and syllables, and other things like intonation contours. We've also seen some corpus resources, different formats in which corpora, the plural of corpus, are housed and in different annotations, different types and as well as formats of annotations that corpora can have. And so in this lecture, we're looking at speech-specific acoustic properties, both articulatory and acoustic phonetics here. Okay. So here are some links to some interesting videos. I actually have links to some of these in a previous lecture, but an X-ray film of articulation and a magnetic resonance imaging film of articulation and singing, and some scopes, some videos of scopes being put through the nose, down the back of the nose, looking at the throat with some fiber optic laryngoscopy. that final word right there. Anyway, take a look at some of these videos. So here's some factors that affect the voice, right? Gender, age, the language you're speaking, right? Obviously, different sounds occur in different languages, right? Genetics can have an effect. The culture can have an effect, right? Like different social groups within one language can use language differently to project in-group identity, right? Your emotional state, or if you're lying, your prevarication, which is a fancy term for lying. Also your health, your voice can be affected by your health, your current state, whether, environment around you, the ambient environment as well. Even recently consumed food can have an effect on your voice as well. Vocal training. So here are some different ways in which people modify their voice, often for singing. You should take a look at some of these. Vocal fry is interesting. Maybe just play a snippet here real quick.
Zooey Deschanel talk, you'll notice they share a similar speech pattern in that they all tend to fry.
Right, linguistic terms, that's called creaky voice. Oops, that's the one I just played. Creaky voice. Falsetto you're probably familiar with. Whistle voice is interesting. Mariah Carey does this. Sounds like she's like screaming, but she's doing what's called a whistle voice. And here's a good explanation by this.
Many of you have come back and said, I want to get into whistle voice.
Anyway, he has a good explanation of what it is and how to do it. Chest voices versus head voice. Here's a funny video of this kid yodeling in Walmart. So he's jumping up into like a head voice. Their breathiness, breath voice, like Marilyn Monroe did.
Particularly with a breathy voice.
Anyway, so kind of a silly one there, but this throat voice is really interesting. You guys need to take a look at this one. Here's a TED Talk. Let me just play a little bit. Jump forward. So they're just using their voice right there to make all those sounds. Anyway, take some time to look at these. They're really interesting. So yeah, people can modify their voice for various reasons. For often singing. So let's talk about pure versus mixed tones. Most sounds aren't pure in the sense that there's only one sound going on. So on the top right or the right part of this slide, we have 3 waves. We have a 100 hertz wave, sinoid wave right here. And then we have a 200 hertz with a smaller amplitude and 300. So the frequencies are different, right? Getting progressively higher and therefore more peaks. And if you just combine all these, add these up, vertically, you end up with this down here, the bottom combination. This is a mixed tone or a mixed wave. right? So it's simply the sum of all of these, whether it's above or below the origin line, will affect where it ends up. But so that's usually what we hear. And speech is an example of this, of mixed tones, rather than just one pure tone. If we had like a tuning fork, that's when you get like a pure tone. There's no other tones going on. But in the vast majority of the cases, the sounds we hear are mixed tones. And it's a complex waveform like this. And organs can have many, many different mixed tones that go into the creation of sounds with organs. And so speech waveforms, let's talk about that. It's a representation of speech intensity over time. Okay, so here we have an H, the top waveform right here is an H. And here we have an E, here we have a A, and an E. Okay, and you can see these are waveforms like in the LDC logo itself, the Linguistic Data Consortium logo. That's actually a spectrogram right there, now that I'm looking at that closer. But these other ones are waveforms. Okay. So yeah, it measures speech intensity over time. And you can have periodic or aperiodic. So periodic is when there's like systematicity, like with vowels. There's this periodicity is the technical term, where there's these cycles or periods that repeat, and they're very similar to each other, one after the other, during a certain segment of the sound, right? Whereas aperiodic or aperiodicity are sounds that have just kind of random jaggedness. There's not a whole lot of like systematicity or patterns that you can find. For example, h, right, is aperiodic, whereas E is periodic. So a spectrogram is a way to look at the intensity, like the frequencies and the intensity of frequencies across the sound. So we're usually interested in the separate components of the speech signal, and it's not very obvious from the waveform. The waveform can show us, let me back up one slide. The waveform can show us some stuff, but it doesn't show us a whole lot about the frequency. Okay, and so there's a mathematical operation to pull out the frequencies out of a sound, and that's called the Fourier transform. And it's a mathematical, here if you want to knock yourself out with the math, it's a mathematical formula or algorithm to create a spectrogram or look at the frequencies in a sound. And the fast Fourier transform is classified by the National Science Foundation as one of the top 10 algorithms of the 20th century. And it's used not only in sound, in speech and acoustics, but in other applications as well. So the idea is that you sample a signal over time. So looking right here in this, the red line is a waveform. You can see this is the combination of those three sounds, the 100, 200, and 300 hertz sounds from before, or something like that. You can see back here that they're pulled out individually in these purple and pink waves back here. And so if you combine them, you get what we see here in the waveform. But if we separate out the frequencies of this sound, we can see that there's this blue peak here for this 100 hertz sound. There's another peak here for this 200 hertz sound, and there's this other blue peak back here for this other component of the mixed sound. So it's a way to look at where is the majority of the frequency happening in a mixed sound. It splits it up into its frequency components. You can plot those component waves in a frequency domain. Okay, so that creates a spectrogram. And so down here you can see that with this discrete Fourier analysis on the bottom here, we have kind of peaks at these points in the frequency band. Okay, here's the waveform. So it's kind of another way of looking at sound. So the waveform looks at amplitude or intensity, whereas the spectrum or spectrogram look at where the frequency, the majority of the frequency is happening. At what frequency are the sounds coming in at? So again, here on the top we have a waveform. On the bottom we have a spectrogram. Okay. So they're both over time. The x-axis is time, and here we have frequency, whereas here we had intensity. So this looks like it's probably a sibilant or some type of fricative here, where my cursor is circling right now. And this looks like a vowel. We have a nice voice bar there with some formants going on there. F1, F2, F3 probably. Well, that's probably 2, 3, 4. F1's probably down there. Okay, so here's some tutorials I have links to about how to read spectrograms. Here's some examples. Again, we have a waveform at the top of A, E, I, O, U. And then we have some spectrograms down here below, as well as what's called a power spectrum here on the bottom. But you can see that there's different ways of looking at where the majority of the frequency happens. So for example, with A, you can see that there's intense amount of sound down here at this frequency, really low frequency, and there's some more at this darker band, and then some more up here, and a bit up there. But let's jump all the way to E, where we can see that the frequency intensity of frequency is different at different frequencies. Okay. So F0, or pitch, is the lowest frequency of a periodic waveform. And it's a proxy for pitch, but you'll just hear people kind of equate F1, or fundamental frequency, with pitch as the same thing. Okay. And that's totally fine just to consider them as the same thing in my mind. And it's perceived as the loudest pitch, the loudest frequency of a sound. And it is estimated via various algorithms. And here's a nice explanation of how that works, a good animation of how you estimate the fundamental frequency of a sound. This video, let's see if I can play something that...
He gets less. And correlation is a very simple function, which is going to take correlation.
Anyway, take a look at the first...
There it is, and it's just shifted.
The first minute or two is awesome there on that video. And so the unit of measurement of the fundamental frequency or pitch is the mel. There are 1,000 hertz and equals 1,000 mels. And 500 mels is half the pitch. So pitch in language, right? The range, the vocal range of F0 in male adults, right? Male adults usually have lower pitch, lower fundamental frequencies than female adults, because, on average, male adults have longer vocal apparatuses or apparati, whatever you want to say there, and so the voices that sound lower with males than females. Now you may know really tall females, and you may have heard their voice as being lower. Like if you see, just take an extreme example, like on some documentary about the tallest woman out there, who's whatever height she is, I'm not sure, 7 foot or more or something. Her voice sounds like a deep male's voice. That's because she's so tall and her vocal tract is really long. There are other factors that go into pitch in humans, but the basic idea is that the longer the string, the vibrating string, the lower the pitch will be, right? And the vocal folds are those vibrating strings, so to speak. Okay. There's other things that go into pitch, right? Hormones, mood, emotion, but a big one is vocal tract size. Intonation contours also, right, can be fluctuated in order to move pitch up and down, right, to convey something in language. Like down here at the bottom part, we have a waveform, and we have down here at the bottom tier is the pitch contour. So it says, I met a really interesting guy last night. Really? Right, so the last two reallys right there differ in pitch, and you can mark those with the pitch contour. And Pratt, for example, shows you pitch contour, and other software does too. And obviously tonal languages make, vital contrastive use of pitch to convey different meanings. So here are 4 words in Chinese: mother, hemp, horse, and scold. and they're all just ma, but different intonation, different, tones. And I'm not going to try and imitate these, but a high tone versus a rising versus a falling then rising, and then a falling, right? So those in tonal languages that use tone to contrast meaning between words, the pitches are highly important, obviously. So resonance, let's talk about resonance here. When an external force drives another system to oscillate with greater amplitude at specific frequencies, that's what resonance is, right? And that happens in sound. It happens with tides, right? Tidal, forces in the ocean. I'm pointing towards California, 500 miles that way. In musical instruments, as well as the vocal apparatus of a human. There's usually more than one resonance, and the harmonics are the fundamental frequency plus and the overtones. What are called overtones or harmonics. And so the fundamental frequency is called the first harmonic, and the second harmonic is the first overtone, just to distinguish those. But harmonics and overtones are often used almost interchangeably. And here are some good videos to explain what those are, what the harmonics are, or the overtones. Just give a quick preview of one
Hey,
of
it's
them.
Andrew Huang. Today's video is about the #1 most mind-blowing thing I've ever learned about music. It's absolutely fundamental to how sound works and growing up in a music we like, but
Anyway,
learning
it's talking
while I
about
was
harmonics. So he goes through different tones. These are harmonics of that first fundamental tone on the far left. Anyway, take a look at that one, this other one, if you like as well. So yeah, musical instruments have harmonics or resonance, and the inner ear of the human, humans have hair cells that detect resonance. And so here's some overtones of A, 440, which is the A below middle C on the piano. So here is the fundamental tone at this frequency, 440 hertz. And here's the second harmonic, or the first overtone to be technical here. Again, the first harmonic is the fundamental tone. The second is what's called the first overtone, etc. Anyway, you can see that it's a multiple of this bass frequency. It's twice the frequency right there, right? And the next one is 3 times this bass, if I'm remembering. Yeah. Yep, 3 times. I'll just do the math real quick. That times 3 is that. Good. Anyway, so the idea is that you're going up in multiples of the fundamental frequency. 2, 3, 4. So, okay. So that is what harmonics are. So formants, I don't know if you've heard formants in phonetics class. The formants of a vowel are the harmonics of the vowel. So the vocal tract itself has resonances. Okay, it's not a pure tone. We don't produce pure tones with our vocal tract, vocal abilities. And the first 2 or 3 formants are the most important for analyzing speech, especially F1, which is formant 1, or harmonic 2, that is the first overtone, and F2. Give you an idea of where a vowel is pronounced in the mouth. Okay, different formant structure, right? Different vowels, that's how we produce different vowels. So an E versus an A versus an O or an U or an E. Our tongue and our jaw are doing different things, and the configuration that those are in causes different fundamental frequency in F1 and F2. And F3 and F4, but again, F1 and F2 are probably the most important when looking at vowels. So typical values for a male, adult male saying that is schwa. The F1 or formant 1 is at about 500 hertz. F2 is at 300 hertz, or excuse me, that's 1500 hertz right there. F3 is at 25 hertz, 2500 hertz. So yeah, like I just said, moving the different articulators changes the configuration of the cavity, which causes different resonances. And once you get above F3, the resonances are so slight that they're very faint, and they don't do a whole lot for us. in the study of language. So let's look at some vowels. So here we have I, E, A, O, U, and U, and U. Right, so here's F1 of E. You can see it's pretty low. It's, I don't know, maybe about 200 hertz or give or take. Whereas F2 with the second arrow is above 2000 hertz. Right there. So E, the F1 is really low, but the F2 is quite high. Let's jump all the way down to A, down here right below it. You can see F1, this first arrow, is what, maybe at 600, 700 hertz, and F2 is maybe at 1200 hertz. So they've come together quite a bit. Okay, so that's how we can distinguish the sounds E and A with those different formants or resonances or harmonics. And so, yeah, that's how you identify different vowels, is with those first two and three, but especially two formants. The third formant is the third arrow on each of these graphs. These plots, these are spectrograms. Okay. So, and here's kind of a simplified view of what we just saw from Latifoga and Johnson, 2011. They just simply put where these different formants are, so F1, F2, F3. And you can see that with E, the F1 and F2 are very far apart, but with A, they're very close to each other. And F3 is quite a bit higher up here with A, but with, or the difference between F2 and F3 is big here in A, but slight, less so in E. Those are just two examples of the vowels. So you may, let's take a look here. So if we look at E and I, the F1 is quite low. And with U and U, they're quite low as well. But with A, it's up at 700, and O at 590, and A at 690. So the idea is that the F1 is inversely correlated with height, the height of the vowel in your mouth, like where it's pronounced. Because E and U are high vowels, and so these are inversely proportional to the F1. Right, so the higher the vowel, the lower the F1. And then F2 is usually correlated, is correlated, that is not usually, it's correlated with backness, how far back in the mouth. So with E and I, those are front vowels. And if we move back farther in the mouth to A and A and O and U and U, we go farther, keep going farther back. Not quite in a linear pattern, but we go back with F2, right? Again, these are inversely correlated with backness, so the farther back, the lower the value is. The farther front, the higher the value is. And so that's how people know where a vowel is being produced in the mouth, using these F1 and F2 measurements, or formant 1, formant 2, which are the harmonics. Okay, so like I just showed, E and I have really low F1, as do U and U there, because they are high vowels. But these vowels are not high. These are quite more open, and their F1 is higher up. Frontness of the vowel, I just mentioned that, right? You can see that the frontness of the vowel is measured, is captured with F2, the second harmonic. There. Okay. And these are used to classify vowels and distinguish vowels and put them into a vowel formant plot like this. So we got heed, hid, haid, head, had, hood, hood, right? And so these are, this is an inverse, right? It's going from larger to smaller on the x-axis here. And so this creates what's often referred to as the vowel triangle. So on the left-hand side of these vowel, on these charts, we would see the front of the face, right? And on the right would be the throat back here. Okay. And yeah, so the vowel charts, vowel triangle charts are constructed using F1 and F2 formants. F1 being the y-axis and F2 being the x-axis. And there's there's variability. It's not, we don't pronounce each vowel in the exact same spot every time, and so there's variability, and so often you'll see ellipses marking where like 95% of some speakers' vowels for this vowel end up, and that's often marked with an ellipsis. For example, here, there are different ways to do it, but I've seen like 95% or 90% of that ellipsis captures that vowel, and so you can look at the approximate region where these vowels are produced by a given speaker. Okay. Linear prediction coefficient analysis is a way to kind of smooth out a spectra. So here we have kind of all the jaggedness, the mixed tone, right? You can see that there's kind of, an intensity, or like what's the word here? A peak of frequency right in here, here, and in here. And what this analysis does, it kind of smooths out the peaks so we can just see where the majority of the frequency is gathered across this mixed sound. Like what sounds went into making this mixed sound. We take this sound, this frequency, and this frequency, put them together, and we get our combined mixed sound. Okay. So this is called a smooth spectrum with peaks there. And here are some examples of English vowels: he'd, hid, had, had on the left-hand side, right? With these smooth spectra from the linear prediction coefficient analysis there. So here's hid with its peaks, formant 1, formant 2, and formant 3, formant 1, 2, 3, etc. Okay. Consonants. Take a look at consonants. Fricatives or stridents produce turbulence, like friction of the sound. So, for example, on the left-hand side, right? That's a, and the majority of the frequency is really high, like probably even above where we're looking here. We can see a lot of friction or a lot of energy of the sound above, 4,000, 5,000 hertz and going up into like 8,000 hertz. And whereas there's some down starting at about 2,000, 3,000 right there and going up. Whereas f has some turbulence, but it's not as strong as s. And then like in thin, these are voiceless. So you can see in the bottom part of each of these spectra, there's not a whole lot. There's a little bit of darkness, kind of grayish down here in the bottom part. Whereas in the right plot over here, these are all voiced, and you can see that there's quite a bit of darkness because that's the voicing of the vocal folds happening. So z, zh, v, and z. Those all have voicing of the vocal folds, and so that comes up here in the bottom part of the spectrum there. Okay, so you can look at acoustic measurements of fricatives. That's what I spent a lot of my research time in, is looking at sibilants in Spanish. Okay, and you can see that the S, the S, and sh have higher amplitudes than their non-strident f and th here. Okay, and I just point out the voicing. This is often called a voice bar, by the way. This dark band at the very bottom of the spectrum is called a voice bar. Here's h, a voiceless version of the following, and plus the following vowel. So right here in the left-hand part of each of these columns of grayness, we have the h, and then here we have the vowel, the e. So, he, ha, ho. So you can see, like, here's the H sound right in here, and then on the right-hand side we have the vowel. And you can see the formants taking structure a bit right there in the vowels, but there's not really much going on with formant structure with the voiceless aspiration there. But you can see that there's some differences. There's anticipatory placement or regressive assimilation, where this H is somewhat affected by what's going to come after it. Okay. Assimilation. Transition, open syllables. We got ba, da, ga, and these can be graphed like this, where we're looking at the frequency and what happens going from a stop, like b, d, g, into a vowel, an ah, and what happens with the frequencies there over time. You can see the voice version, b, and the voiceless version. So voice is, there's vibration in the vocal folds, whereas p, there's no vibration in the vocal folds with the p. Excuse me. Here's some more examples of different syllables. Be, 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 ba, ba, bo, bu. And you can see with the F, the frequencies F1 and F2 happening there. Some more examples of spectrograms. And you can see burst happening here. So this is hid, had, head. And you can see this is just simply the waveform the waveform here. And the D over here. Each of those in a little burst. From the stop, here's some more examples. So connected speech is fascinating because sounds are affected by their flanking sounds, their neighbors. It's a fluid thing, and so there's assimilation between sounds a bit as you go along in connected speech. That's one of the toughest things to get right with text-to-speech software, is getting the transition between sounds to sound natural rather than like stilted, like robotic type sounds. But companies are doing pretty good, like Alexa and Siri are doing pretty good with their ability to do text-to-speech software. Here's some more formants of hide across the whole word hide. You can see the over here on the left-hand side we have the H, the aspiration. There's no voice in there. Then we have I, and then D with that release right in there. Okay, formant and pitch tracking. Yeah, you can look at formants and pitch in Pratt and other tools like Pratt. You can also dump them out into measurements like numbers. You quantify it. So in the next slide, you're going to be looking at waveforms and spectrograms and pitch and format manipulations, like taking out different formants out of your own speech and listen to what it sounds like, taking out some of the harmonics. Let me just real quick back up and give you an example from one of the videos I linked to, but I showed a little bit. Let me see if I can get it quickly here. This one right here does a really good job of showing what happens when you take out formants.
Is a sine wave.
A sine wave is the purest. For a second. I'm going to try and find where
like our guitar
he
sound
shows what
harmonic
happens when you take out. So
the main note that they're playing, the lowest one, the fundamental, is actually completely identical, and it's just the mixture of harmonics that give guitar both playing in tiny little notes. Let's check them out in a spectrum analyzer.
So
these distinct sound, a lot of
what I want to show you
is first overtone. The fundamental counts as a harmonic, and that's the one difference between the terms harmonic and overtone. The guitar's first overtone technically depends if I.
Anyway, the idea there is if you take out those harmonics above the fundamental frequency, the clarinet and the guitar have the same tone. I mean, that's what we're hearing right there. And so you can manipulate, let's go back over here, manipulate your own voice by taking out formants, and it's kind of fun. So anyway, that's the idea with the next lab, is to look at your own voice, analyze it, and do some plots, some spectrogram plots and spectra. Okay, great. See you next time.